So let me share my screen. Can you see my screen?
Yes, I see it. It's not still in the presentation mode, but I see it.
Okay.
There we go.
Do you see it in presentation mode?
Yes.
Okay. That is good. So today's topic that we want to talk about is digital twins of modern power systems. So I'll try to talk about the requirements and some experience that we have gained working with the RTDS users. So my name is Arunprasanth Sakthivel, and I work for the RTDS Technologies for the past almost 8 years. So this is the agenda of my presentation today. I'll start with computer simulation of power systems. I just want to highlight and what type of a system that we are trying to simulate. And then I'll talk about the large scale power system simulation, which is kind of the topic of this task force, and how we can do it in RTDS. And also I'll talk about some examples on large scale RTDS simulations. And lastly, I'll briefly talk about the digital twin experience that we have while working with the clients. Okay, so I put the picture here just to show you how the power system has evolved over the years. And back in the days, we were dealing with traditional power system, which had generation or centralized generation. And then the power was transmitted and then distributed across the loads in power system, right? But looking at the modern power system that we have today and also talking about the future power systems, the generations are added everywhere, not only the generating stations, there are being added in transmission level and also in distribution level. So the power flow becomes bidirectional, and modeling and analysis becomes more and more complex. And I also put this time scale of different power system phenomena that we want to see in a practical power system. Let me see if I can add a pointer here. Okay, so traditionally we were simulating the power system in this electromechanical transient range. So that used to be the time scale of interest. But with inverter-based generations being added everywhere in the power system, we are moving more and more towards the electromagnetic transient range, where we can look at the time scale of switching surges and converter switching and converter controls and so on. But not only that, the time scale of interest is keep on expanding, because we are seeing more and more high frequency switching devices such as electric vehicle and then whatnot. So we are actually moving towards very small values of microsecond range. And also on the other hand, we are also moving towards very slow transients such as thermodynamics, where people are talking about hydrogen-based power generation. So when we are dealing with large power systems, it is going to have all these different dynamics. So we need to be able to simulate them to analyze the stability depending on the time scale that we want to see. Okay, so let's look at how the power system studies have evolved with the improvements or the additions that are taking place in the power system. When looking at the conventional power system, when we want to do power system analysis, looking at power flow studies, we used to do it for full network using a load flow simulation tools. And when it becomes transient stability analysis, major portion of the network was modeled in TSA tools and the studies were done. And when it comes to EMT studies, only a selected portion of the network was simulated. The rest of the network was simulated as an equivalence. and often offline CMT simulation tools are used. And when it comes down to equipment testing, people used or modeled only a relevant portion of the network, and the remaining were modeled as purely Thevenin equivalents. And for that purpose, real-time simulators or real-time targets were used for equipment testing. But moving towards the modern power system, where we have inverter-based generations and resources everywhere, so power flow and TSA studies are done for almost a full network using TSA tools, and EMT studies are done for most of the part of the network using offline or real-time EMT simulation tools. And when it comes to equipment testing, major portion of the network around the study area are being modeled now, because this is the experience that we got from the industry at present. So they model a fairly large network around the point where they want to connect any inverter-based generations or HVDC. For that purpose, the real-time simulators are being used. So let's look at why we want to simulate a power system using EMT simulation tools. So the clear reason is that increased use of power electronics-based equipments in the system. And therefore, the EMT simulation is required for general power system studies, such as planning and performance studies. And also, as we know, the EMT simulations accurately represent the interaction between HVDCs and inverter-based generation. So from the NERC study, they strongly recommend EMT studies to be done for renewable energy integration. And also from the study, they found out that majority of the tripping events when using solar PV inverters could not be accurately simulated using phasor-based simulation tools. So we can take a look at the reference here to find more details. So basically, an EMT simulation tool is recommended for studying practical power system that we have now. Okay, so coming down to digital twin. So digital twin of a power system is a representation of the system in computer simulation tool that generates results same as the actual power system. So this is a very high level definition, but this is what we try to achieve. And the complexity of the simulation model is going to depend on the accuracy that we are targeting from the model, or the frequency band that we want to see, and also the system that we want to simulate. And then depending on the complexity of the model, probably you might have to use high performance computers to simulate such a system to realize a digital twin. And the applications include control and protection testing, control room advice, and training people, and field operation support, and controller reconfiguration, etc. So most of these applications are kind of time critical. So having a digital twin in a real-time simulation tool would help to take those time critical decisions. So having talked about power system simulation and what we want to achieve with digital twin, then it comes down to the requirements. So if you want to realize a digital twin of a large scale power system, there are some requirements for the power system simulator that is going to be used to model it. So the simulator should be able to model sufficiently large power systems, and it should consist accurate component model to represent a system dynamics over a wide range of frequencies. So for example, DC to, let's say, 100 kilohertz or so. And also it should support the use of different integration time steps so that we can accurately represent the time scale that we want to see. And then it should have a time efficient compiler. This is a very important aspect of the simulator, because if a system takes several minutes to compile, then it's going to add up on the simulation time as well. and it should be able to perform EMT simulation within a short time. Therefore, the real-time digital simulators are preferred. And when required, it should be able to allow interfacing external equipment and to do hardware in the loop for some studies. Therefore, we think the RTDS simulator can be used to realize a digital twin of a modern power system. All right. For those who don't know about the RTDS simulator comes from the RTDS Technologies. So we are located in a city called Winnipeg in Manitoba in Canada. And we have about 75 employees doing A to Z of the RTDS simulator. And we have customers we have over 500 customers worldwide. So talking about the little bit of history about RTDS simulator, the RTDS development project began at the Manitoba Hydro, which is the utility in Manitoba, in 1986. And in 1989, we performed the world first real-time digital simulation for HVDC systems. And in 1994, the company RTDS Technology was created. And at the beginning, the RTDS was started as a research project, and now it is kind of an industry standard. And the software that we have is called RSCAD-FX. It comes with everything that we need for a real-time simulation of power system. So that is just a background of the RTDS simulator. Okay, so next I want to talk about the large-scale simulation options that we have when using RTDS simulator. So there are two options available. One is real-time simulation option and also non-real-time simulation options. When talking about real-time simulation option, the entire network is going to be modeled inside the RTDS, and it is a faster EMT simulation, and we can interface with external equipment. It's also suitable to create a digital twin of a large-scale power system. And coming down to non-real-time simulation option, it's often slower than the real-time because we are talking about large-scale system modeling. And it's a possibility to perform co-simulation with other simulation tools to be able to model a very large network. But it's not recommended for interfacing with external equipment. Okay, so how the large-scale simulation is done in a real-time simulation tool? Often we make use of the multi-rate simulation thanks to the traveling wave transmission lines, which allows us to interface networks that are running in different simulation environment or with different time steps. So in RTDS, we have primarily three different time step environments. The main step environment where we model typical power system components like generators, transformers, transmission lines, and so on. The time step would be in the range of, let's say, 30 to 50 microseconds. And then we have a sub-level of time step, which is called sub-step, which is a subdivision of the main step, which this environment is typically used for modeling power electronics. And then we have a simulation environment called super step, which is multiple of the main step, but still used to model EMT simulation network. So these are different time step environments. Depending on a system that we want to simulate, we could choose the simulation environment and then interface them to create a platform for large power system simulation model. All right. So when it comes to simulation of inverter-based resources, often there's a question asked whether we can simulate black box controls. Because vendors often they create black box controls in simulation tools to protect their intellectual property. So with GTSOC, is a FPGA-based hardware in RTDS, it allows us to model vendor controls and run in parallel with the RTDS simulation. to realize a real-time digital simulation incorporating vendor controls. So I'm not going to talk much about it, but just put a slide so that we know we can simulate proprietary controls with the real-time simulation. Okay, so coming back to real-time simulation of a large-scale system. When we take a power system, we could divide it into different areas where we specify area called area of interest, where we are going to apply some transients like faults or breaker switching. And that also going to include power electronics. So we could model the entire system and called area of interest that is going to be modeled in main step, where there is power electronics is going to be modeled in substep to keep up the accuracy. And the remaining network, they can be considered as remote systems, but they are modeled in superstep with fully empty details. So this is an efficient way of modeling a large-scale power system using RTDS as one platform. Okay, so let's put some numbers here just to know how big of a simulation can be done. So this, with the superstep approach, let's look at the capability of the latest simulator, that is NovaCore version 2 chassis. Let's say it consists 10 cores. And let's assume the 5 cores are used to model external network using superstep, as I have shown here. And each of these superstep blocks runs on one core and can simulate up to 120 buses, 3-phase buses. And the main network that is going to have the area of interest and also maybe a substep that can model up to 120 buses. So altogether, we can model a 720 bus network on one chassis. So considering a simulator with 14 such NovaCore chassis, we can model up to 8,400 external network buses and 1,680 main network buses, which gives us a total of around 10,080 buses to be modeled in a large-scale simulation. And the actual count is going to be much more because there are embedded buses as well. But with 14 NovaCore chassis, we can simulate over 10,000 buses, all in EMT that runs in hard real time. So this is just to give you an estimation of the capability. But when scale up the simulator with more NovaCore chassis, this number easily goes up. Is on the second option, RTDS also has a TSA simulation option, so which can be used to model a very large power system. So again, area of interest is going to have power electronics and substep and main step. And then it can be connected to remote system in superstep, as well as remote system modeled in transient stability type solution. So this is again inside the RTDS, which runs in real time. And the interface between TSA and the main step EMT is done through dynamic phaser. So that gives a smooth interface between full EMT simulation and the phaser-based simulation. So with this approach, we can model 10,000 buses, even with one NovaCore chassis, because each of these TSA remote system runs on one core, which supports up to 2,000 buses. So we could easily have 5 of these to realize 10,000 buses, and the remaining can be modeled using main step, substep, and superstep as required. So this is the second option. And the third option, there is also a co-simulation option. The RTDS simulator can be interfaced with the TSAT simulation tool using an interface board, which is again based on FPGA. So the T-set side can simulate up to 5,000 buses. The remaining can be modeled on RTDS. So the interface is done through a GT FPGA and everything runs in real time. Okay, so talking about non-real-time simulation option for large-scale systems. So RTDS has lately worked on a non-real-time simulation mode to enlarge the capacity of the simulation. So basically, whatever you could put on one chassis could be simply put on one core of the Nova core chassis to enlarge the capability. So it gives approximately 10 times larger network that we can model on one chassis to be modeled on non-real-time simulation mode. And the minimum execution time per time step is going to be 200 microseconds. It's regardless of the system, that is the minimum. And the execution time will automatically adjust above 200 microseconds, depending on the complexity of the model. And this option, again, allows us to interface black box controls using GTSOC hardware. And there is another non-real-time simulation option, which is a co-simulation between the RTDS and PSCAD. It is done through Ethernet UDP communication. So there are two options available. One is control signal interface or power system interface using traveling wave transmission lines. Again, this will be useful, let's say, if there is a vendor control that is already modeled in PSCAD simulation, we could easily interface that with the RTDS simulation using this method, but keep in mind that this is a non-real-time simulation. All right, so talking about all those possibilities, I just want to give some examples on large-scale RTDS simulations that have been carried out by the users. So this is an example of the simulator in southern China at Nari NSG Apri. So the simulator capability they have, they have 40 plus Nova core chassis and 16 PB5 racks. It's a very big simulator. And these numbers were, I think, taken from 2020. I think the numbers have gone up now. They can model more than 3,600 three-phase buses, all in main time step. And also 20 HVDC links, they use sub-step for it. And there is a reference here I have put at the bottom. So you can check the link to read more about this simulator and what they can do. So basically, they try to validate wide area protection and control schemes. And also they do coordination of HVDC and HVAC links and controls. And they are testing system stability controls as well. And the reason I have put these examples here, and we know that they are all working on to realize something called or something really close to the digital twin. So that is the reason I have put them here. And you can read more about it in the link given down. And the next example is TAS Network is in Tasmania. So they have a decent simulator which they use to simulate their majority of the transmission system. It's 110 kV and 220 kV system plus 500 kV lines as well. And what they have modeled in their system has been shown here. So they have modeled an LCC HVDC and two MMC HVDCs and 59 synchronous generators with all local controls that they have, and 12 HVDC converters and 136 transmission lines, capacitor banks, substation, and over 20,000 control components, which is mainly used to model generator controls, such as exciters, governors, and power system stabilizers. And they have modeled over 2,000 megawatt of wind and 1,000 megawatt pump storage. So this is another example of large-scale simulation utility. And this is an example from NIPA. They have a big simulator that consists of 6 Nova core chassis consisting of 60 cores. And they have modeled the New York State transmission network. They converted it from P.Sc, and then they keep up the model up to date using the actual measurements. And finally, there is a large-scale RTDS simulator available in TU Delft. And the simulator capability includes 5 Nova core chassis and 4 PB5 racks, and importantly, 40 MMC support units. They're currently working on digital twin of EU electrical system. So these are some of the examples that around the world. I have put only a few here because I could find reference only for a few, but there are many more. They will show up in near future. All right. So coming down to digital twin, so this is our experience. Just going to talk about that briefly. So looking at the difference between the typical simulation model and a digital twin. So simulation models are mostly done by taking the actual data from a system and modeling in simulation model. But on the other hand, digital twins, the same way that is modeled, but they are updated frequently using system measurements. And not only that, but also any necessary decisions that were taken based on the analysis of the digital twin are informed back to the real power system to take necessary actions. So there's a main difference. So we need to frequently update and perform analysis using digital twin and then inform the decision back to the power system. And talking about the use of digital twins and how it is done, I have already mentioned there is a power system. We take actual measurements. It's an energy management system. And then usually the energy management system will make the data available in a readable format. We call it as snapshot data. And then we use that to model the power system or update the power system, and then do analysis. Before the next snapshot is available, we have to complete the analysis and then report the results back to the energy management system, and any setting changes will take place. So the main purpose in our application was to de-risk the cascading blackouts that could result significant damages to the system. And one of the application is to check relay settings every hour according to the data from EMS. So that is one main application, I would say, because as we know in present power system, the power flow is bidirectional. Any change in the network is going to change the power flow on the system. So the relay settings might have to be changed. So based on our analysis, we already found a hidden error in an impedance relay, and we have helped them correct it. So in this presentation, I don't have details to mention about the customer that we work with, and also I don't have any results because they are not available public. But in another installment, if I get a chance to present, then probably I will have some more results about it. Okay, so the procedure what we did, we built the entire 345 kV transmission network in RTDS and update the network configuration using the online data from EMS. And the model also included all major relays modeled inside the RTDS, and the relay settings were read from the file generated by the user. And then some of the relays were interfaced with the RTDS simulator in hardware in the loop. And using this model, we performed contingencies to validate the relay coordination of the entire system. So the actual challenge was to update the case using external data in a time efficient and automation manner. So what we did was initially the network was available as a PSSC simulation model. And in RTDS, we have a data conversion program that can take the model from PSSC and convert it to RSCAD. That created the base model in RTDS. And then from there, we can export the data as CSV files. So that is going to be the database for the entire system. And then from EMS, we can get the snapshot data. And then we developed a Python script that can read the EMS data and then update the database. So create a new database with all the important changes. And then that can be imported into RSCAD to get the updated model. So this was done hourly basis. So all the analysis and contingencies were done within that time so that we can do the analysis for each snapshot. So this is where the real-time simulators was helpful because they produce faster EMT simulation so that the analysis is faster. Okay, so updating the power flow data is what the Python script does. It reads RSCAD component list, and for each component, it maps the data from the component to the snapshot data, and then it writes the updated information into a new database file. And these are some of the parameters that were changed based on the system snapshot. And the detailed procedural framework is shown here. Primarily, the conversion program was used to generate the base model. And then in step 2, we created a mapping between the RSCAD component data and the snapshot data. And then step 3, the data was exported to a database from the RSCAD simulation. And then in step 4, we run the case and monitor the variables. And then from the EMS, it generates a snapshot, which was available in the raw file format, which is again the PSSC format. And then the Python was used to map the data between RSCAD components and the snapshot data. And then it generates a new set of database files or CSV files that gets imported into RSCAD. And then we compile and run the new simulation model or updated simulation model. So we repeated step 4 to 7 and run the contingency list of the cases and check if the relay settings meet the requirement for changing the power system. So this is the procedure that we carried out, and basically that is the experience that we got from the RTDS. For this kind of time critical analysis, it is better to have a real-time simulation tool so that we can finish all the target studies within the time, which means within the time frame where the EMS generates snapshot. All right, so basically that's everything that I have, and the takeaway from this presentation is that power system simulators have significantly advanced, and now it is possible to perform EMT simulation studies of large power systems. And also power system modeling and simulation techniques have improved. So we can optimally utilize the processing power of a computer to efficiently use it to model large networks. So the RTDS simulator today is an all-in-one real-time simulator that meets all the requirements for a simulation of modern power systems. And the real-time digital twin of a large power system is within reach. All right. Thank you, everyone.
Arun, thank you very much for the interesting presentations. This was very interesting to me, especially from the slide that you started differentiating between the concept of model and the concept of digital twin, and then you expanded on that and showed us some examples and experiences. Thank you again for that. I would like to open the floor for questions from the audience. So feel free to put your questions in the chat or just come off the mute and ask your questions verbally. Professor Polinsky, go ahead, please.
Yeah, hi everyone. Sorry, my camera is broken. Thanks for the presentation. I have one question. You mentioned that you do this co-simulation with transient stability and RTDS and dynamic phasors. And I wonder about the workflow. So if I have models in EMT, in RTDS, can I convert them automatically into the TSA domain, or do I have to model and validate that myself manually?
Yeah, that is a good question, Professor Peter Polinsky. And yeah, the answer is yes and no. So basically, there is a export feature in RSCAD which allows you to export the data in PSSC format that we can use to model the TSA simulation. Basically, the TSA simulation in RTDS requires PSSC files, which is power flow and the dynamic data file to model. So basically, we need to generate the portion of the network in PSSC format to be used in that co-simulation platform. I'm not sure if
All right,
I
thanks a lot.
answered it.
Yeah, perfect. Thank you.
You're welcome.
Thank you, Peter and Arun. Any other questions from the audience? Maybe while folks are thinking about their questions, I can ask one of my questions, Arun. So you gave us or showed us some a few of the examples that basically you guys at RTDS experienced using digital twin to solve the problem. Is there any other application that you envision for the future for the digital twin that can become helpful to solve any problem? Something that you haven't experienced yet, but you think in the future it will come and it will become handy and useful?
As far as I can think, basically people want to use the digital twin as a SCADA-based system, because whatever you observe in the control room should be able to be done with the real-time digital twin. So that is where everyone is moving. That's why what my feeling is. So that's the reason, like I was trying to convince everyone that the real-time digital twin is what we want to achieve at the end.
Okay, and in the example that you presented, I know that you get some information from the EMS system. What kind of information are there? Are they only measurements of, for example, load levels? Do they impact the topology of the model that is running in RTDS, or no? For example, is there any breaker status measurements that goes into that to change the topology, or no? It's just the measure. The topology is the same. Only the load levels or dispatch levels or things like that change.
The data from the snapshot data from EMS has both the load changes, generation changes, and also the network. For example, if a transmission line is out of service when the snapshot is taken, and it will show as out of service in the snapshot data, so that in RTDS simulation, all the branches and shunt connections or sources, everything were modeled using breakers. So if the Python script finds that the snapshot has a branch that is out of service, which was in service before, and it's going to open the breaker for sure. That's how it was done.
But I assume that if there is any change in the topology in the sense that a component is added or removed, or let's say a generator power plant is retired, those kind of things will have to happen manually, has to be reflected manually in the RTDS model, right?
That is correct. For now, yes, that is how it is being done. But that is something that we can put in the plate to for further thinking.
Got it. All right, I see Dr. Sanjeev's hand up. Sanjeev, go ahead, please.
Yeah, thanks, Hussein. Thanks for the nice presentation, Arun. So sorry for the background noise. So the one question I have is from the GT SOC, So the GT SOC is basically meant for the black box controllers, but do you have any vendor-based controllers by default as a model length that we can test and perform for different things? Or we need to really work with the vendors to get them model just dump into the GT SOC and then use it. I never used it. I'm just started using it. So I want to know more on that side of it.
Thanks for the question. Yes. So we have built a Simulink controller by ourselves and converted it to a .a format and using it in GTSOC that we have been sharing with the customers, but not any vendor controls. We have worked with vendors. I don't want to lie, but those models we cannot share. But there is one more thing that in upcoming SIGGRAE conference, I heard that there's going to be a presentation on how a vendor control was modeled in RTDS. So this between HVDC vendor and the RTDS. So there is something coming up, but to get a controller, a vendor controller, it's better the user have to work with the vendor to get it.
Yeah, thanks, Arun. And the other one is just for your FYI. So, Enril also has more than 22 simulators, RTDS, including the Workout 2.0 and all the way from PB5. So, and we do have a couple of FPGA and a lot of things. So, if you want to include that as one of the largest digital twin simulators, so you can also include it, but I can provide you the more details on it. Yeah, thank you.
Sure. Yeah, that will be helpful. Yeah, I was looking for references. Like all the time when I want to put some numbers or any experience from the user, I always find reference. That is the good way of doing it, I think. So I didn't find a reference, but it would be great if you could send me the reference. I can include it in the slide.
Sure, Arun. Thank you.
Yeah, that's great. Thank you.
Thank you. Peter, your hand is up. Go ahead, please.
Yep. Yeah, with twins, it's always the workflow that is interesting. And my second question is regarding that. You showed your use case of these updates coming from the EMS. And I was wondering how fast this comes, what's the time step? Because sometimes when you talk to people, what they see as a twin is usually their romantic view of I have a digital replica that shows exactly what is out there and I can compare it and see differences and maybe fast forward or go back in time. So that's what people believe when they have it. But for this, you would need to have permanent stream of updates and as fast as possible synchronization with reality out there on the fly while the solver is running. Huh? And as far as I understood your case, it's more like you get the EMS data, update the files, compile it and run something like your protection relay sanity check. And then when the next update comes, I don't know what's the time step, but probably it's, I don't know, an hour or so, or 20 minutes. Then you do the next case. Is that correct?
That is correct, Professor. Yeah. So the EMS data comes every hour, and we try to do the contingency, a list of contingency within that hour, and produce the results for each snapshot.
All right. And how would you, well, when you dream a bit, how would you update a running simulation? So if I would ask you to give me an RTDS case that runs, and I would like to update on the fly while it's running parameters or breaker states and these things. Do you think that's possible at all, or does it violate some fundamental architecture decisions in RTDS?
Yeah, currently I don't think it is possible, because if we want to change a breaker, changing loads is possible, but changing network topology while the case is running, it is kind of, we have to recompile on some of the models. But the study that we did, in that the case was stopped after the contingencies were done and the data was imported from the CSV, and then the next set of simulations were run. But we are also working on to generate a full Python script that can also update the system parameters. But it's not completed yet, so I cannot guarantee if we can do it while the simulation is running. But we are working more on that to be to make more automated.
All right, thank you.
You're welcome.
Thank you both. Any other question from the audience? Okay. Before we close the session, and while folks are thinking if there's any other last-minute questions, again, this presentation together with the previous presentations will be available at this link. I just put it in the chat. We recorded this presentation, but due to the size and volume, we cannot upload it on the website. So I'm going to send a link to anyone who is registered in this task force to get a link if he or she wants to watch the video. With that, last call. Any other question for Arun?
Hi. Hey, this is Farzal from University of Louisiana.
Hey, Dr. Ferdowsi, go ahead. Yeah.
I missed the first 20 minutes of the presentation. Sorry if that's a repetition. You already addressed it. My question is, if I'm a decision maker in industry, power industry like utility, let me put it this way. The amount of investment and the type of investment for starting digital pointing is a really important thing to know for a decision maker, right? Like how much I need to invest in this. So the first question is, where should I start from? Like DR, interconnections, or transmission, distribution, where I'm starting from, and also what amount or what type of investment I need to make for this. Thank you.
Okay. Thanks for the question. And as far as I think, mostly people or utility people will start from their transmission network. So at least they want to model the majority of the transmission network, because losing a transmission network is more critical than losing a distribution. So based on my understanding, generation transmission is what we need to model. The distribution can be equalanced. But again, within the transmission, there are different voltage levels. So we have to start from at least the highest voltage and then come down to expand the network. So this is what I think. So you have to know how many buses you're going to model. Let's say above 500 kV, then start from there and then add 220 kV, 110 kV and come down.
Okay. Thank you, Arun. Do you have any other question, Farzad?
No, thank you for the information, and special thanks to Sain for leading this task force. Appreciate it.
Of course, appreciate it. Jean-Nicolas, go ahead, please.
Yeah, hi. Very good presentation. Thank you. Just to mention that Opal RT also has been working a lot on such solutions in the past few years. I just wanted to add a comment to Mr. Ferdowsi, sorry, his question. I guess it's not just about the cost, it's also a cost-benefit analysis you need to make. Probably if you work in a utility, you'll need at one point to consider if you want to really represent the dynamics of your system properly so that you will avoid blackouts. And it seems like in cases where you have large penetration of IBRs, you will need to go to EMT simulation at some point. So maybe if you start with the cost of not having the right dynamics represented in your model, and then you go into what is the cost of such a system or such a digital twin, it may give you a good idea. I don't have a clear answer. It's very general what I'm saying, but I think it's part of the equation as well.
Good point. Yeah.
Thanks, Yi.
Thank you, Jean-Nicolas. Any other questions or comments? If not, then I thank you all. I specifically thank Arun for the presentation. And I think we're going to have 2 or 3 more presentations until the next general meeting. I will send out information as soon as I basically confirm the presenters. With that, I again thank you, everybody, and I hope you have a great rest of the day or rest of your evening.
Thank you, everyone.
Thank you. Thank you, everyone. Bye-bye.
Thanks, everyone. Bye-bye.